All right, welcome back to Light Demon Programming. So let's start actually working on our compiler. So we're going to be dealing with the parser. I want to make sure I'm in the right project here. Yes, I am. Okay. We're going to be working with the parser and the abstract syntax tree code and the Lexer for now. We will visit the drivers and stuff and how we operate that soon. But for now, what I want to do is go into my abstract syntax tree. 1 second here. And make a little bit of an update. So let's go in here. And so let me describe the abstract syntax tree. First, there's a base class, expression AST. And a number AST is an expression AST. It contains a double value. We'll have other kinds of numbers probably at some point, or we'll figure that out. For now, we're going to keep it simple. We've got a variable expression AST. It just has a name. Later, we'll work on how we keep that in a table with values and other things and assignments and so forth. And then we have a binary expression AST. It has an operator and a left-hand side and a right-hand side. And then we have that's the function call, and then some other stuff, call expressions and prototypes. We'll get into those later. But call expression is an expression. We're going to have to update that one. So a call expression just has the name of the callee and a list of arguments. And you'll notice in here that these are all housed in unique pointers. So that stores a unique pointer in there. I created some functions here to help make them. Instead of having to call this kind of thing all the time, we just call this make expression and pass it the value, and it calls standard make unique, which makes a unique pointer pass of that type and passes in the value. And you can pass in any number of args. It's a template class with variable arguments to it. So we use this all through. So what I want to do now is be able to print out what's going on with my expressions. Okay, so what we're going to do is here in this top level one, we're going to create a virtual method. And we're just going to call it out. Standard OStream. Ampersand OS, and that's all that's going to take. And we're going to set this equal to 0. This needs to be a constant and needs to be equal to 0. Okay, so this is a virtual function. All our classes, if we try to compile now, there's something else I need to do. Anyway, we get a bunch of errors because we don't have this overridden in these other classes. So let's do the very first override. And there's something that I need to do here. I need to go go up here, get checkout minus B. Episode 2 end. There we go. We're in the episode 2 end branch now. So that when we get done with this and I write it into it, it'll be all in that branch. All right. So we need to override this. So let's just copy it. Put it down here. Get rid of this part. We'll make a function out of this. And what are we going to do? Well, if we want to send out this, all we really need to do is send out the value. So we can go OS from val. That's simple. Let's pop it into this one and see what we need to do here. This one's just going to be OS from name. And we'll pop it into here. This. Now, this is a little more tricky. Take a quick look at my notes here. So, unique pointer is a wrapper for a pointer to some kind of an expression. So, what we need to do is go OS from, and we want to look at the left-hand side, LHS, and if we do pointer, oh no, we don't want to do OS. We're going to do left-hand side, pointer, out, OS. So we're going to call this out function on the left-hand side and pass it in the OS. Then we can do something like OS from quote space quote. And then we can go OS from op, which is just a string. Then we can go OS from quote space quote. And then we can go right hand side pointer out OS. All right, so what does this code do? When we call out on this, if there's the left hand side expression is called, and it calls out on that, so it's going to do whatever that left hand side object is. It's going to put it out, and it's going to put a space, then it's going to put some operator, whatever the operator is between the left hand side and the right hand side, and then it's going to put another space and the put out the right hand side. And then well, we can go ahead and do this one. We're not going to use it. Oh, that's make binary operator. What's this? Binary expression, make binary expression, and then we have the call, AST. So we need to put it in here, but I'm not going to do anything with it right now because we're going to work on this later. We don't have anything building this or creating it, and then prototype doesn't need one right now. So this should now build. Go make, oops, cd build, make there it is, it built. So now what can we do with these out methods? Well, we can come over here. Well, one of the things that we could do very possibly here is have a I think to do that we'd have to have a friend class on every one of them. Yeah, we won't do that for now. I'm not going to deviate from what I've already planned. I've done that before and I get all messed up. So all we have to do here, so here we're building, so when this parses, it's an expression or a program followed by an expression. This is what our test file looks like right now. It's just a bunch of expressions in a row. So, or it's a module code followed by an expression and so forth. And this is what's happening inside of a module. Program expression module code. Oh, I'm not using this yet. We'll work on this later. Right now it's just an expression followed by or a program followed by an expression, which is down here. So an expression could be a floating point number right now, or an expression followed by an op followed by another expression, which can be binary expressions just like this one. So we make whenever it matches a float, we make a number expression and pass in the number, and that's creating that unique pointer, which is being assigned to the $$ slot, which is where this type right here comes from. This expression is of this type, so it can assign that pointer to it, that unique pointer to it. And down here under this, we make a binary expression where we give it the operator, which is position 2, if you remember, and then we call standard move on $1 and standard move on $3. And I'll explain move well, I'm not going to explain move right now. Just take it. I'll give you the basics. It's going to take that unique pointer that was collected previously and move it to whatever this one is. So it's now like the owner of it. Think of it that way. It's getting moved into this spot. And we could do that over here. Let's see if where's binary expression? There's make binary expression. Here's binary expression. Oh, standard move. All right, you know what? I don't have to do it there because I'm already doing it here. And that's actually the proper place to do it. So I'm going to take those out. I'll explain the move when we take a closer look at the AST. This should work. Let's build it again. Yeah, that's fine. So whenever we get a float, we want to go like this. We want to go $$, and we're going to use the pointer dereference out, and we'll pass it standard C out. That'll be the stream we'll use. And we can do the same thing down here. The difference is that down here we're going to go standard C out from and L. Let me double check that, make sure I did that right. Yeah, and if it's just a float all by itself that we're printing out, we'll also do that here. We'll put the standard C out from end L there. So let's make this and see what happens when we run it on our file. Oops. And oh, that's right. And L. And that's good. And now where's our let's get push, get commit, get add. Okay, it's back there a ways. Source Socrates -I .. slant source slant test .soc, and there it is. So what happened here? Well, our parser ran. It parsed each one of these, and we can prove that that's coming from the parser by going in here and we could do something like OS from binary expression. Let's do that. So the expressions that are just numbers will just be numbers, but this one should show, see, so it's parsing it. It found binary expression. It created the node for it. When it printed out that node, it did this. So we've got that kind of working now. We can see what our abstract syntax tree is doing, and we can see that binary expression is definitely working. 3.2 plus binary expression, 9.7 plus 8.5. So if we don't have this in here, it won't put that break in. Let's take that out. So we can see that this is a binary expression, and this is just a number expression. So this tree it's captured a binary expression, and it's the left-hand side of another binary expression which has this float in it. So they're in a tree. They've formed a tree, and it's working correctly because that 3.2 plus 9.7 plus 8.5 should be what's in our test file, and yes, it is right there. It captured it exactly, and it reproduced it exactly what we put in here. What? .5. Oh, because it's finding okay. The reason for the duplicates is it's finding the float and printing that out, and so we could take care of that. Uh, well, I don't know if I'm going to worry about it too much. We could just take these out and it wouldn't print the floats that are on their own, but in a way they are an expression. Well, I'm not going to worry about it. I'm not going to deviate. Excuse me. I've got to stick to my plan here, or the flow of the thing gets all messed up. I want to turn this off and check the time. How are we doing? We're 15 minutes in. So let's talk a little bit about the abstract syntax tree then. So the abstract syntax tree, I kind of went over this briefly, I guess. We're building it up. We've got these make functions here to create the individual nodes, and we're building them up by passing them in. We'll have different kinds that will take different nodes in them for different execution processes. And we kind of went over what an AST was in the previous videos. If, by the way, you haven't watched part 1 of this series in the playlist, Compiler Design, you really should go check that out. A lot of how this kind of thing, like abstract syntax trees work, is covered in that. Let me get rid of that. So one of the things we're going to be adding to this is the ability to generate code. But first, we've got to generate some other stuff. We need to be able to create a call expression. Oh, and you notice, well, I just all used pluses in that. Let's add to this. Let's do some other symbols. Like if we went let's go 5.9, and then let's have a special. Oops, not that one. Let's have a special symbol, 2.6. So we're going to be able to create operators of our own. Let's run that. And there, it actually captured it, and it captured that as the operator. So we're going to have multi-character operators in this language, and the ability also to define operators. For instance, you might have something like as an operator. And there, it produced the operator down here. Hopefully you can see that. I don't think, no, I can't expand this. I can't expand this either. Oh, that's right. I can by doing this and finding. We want to is it font? Zoom in. Editor font. Zoom in. That's it. I don't know if it does it to all of them. It did do it to all of them. Okay, I'll try to remember to do that and keep this a little bit bigger for you to be able to see. So our parser, our Lexer, then, I don't have it open, Lexer.l. Our Lexer is capturing operators by this regular expression. All those symbols are going to be valid operator symbols. And you can have more than one, at least one, you can have more than one of these symbols in an operator. And then, of course, there's identifier, which I also have a sim 1 for. Might do that a little bit differently. We'll have to see. Oh, I think I intended for sims to also contain dots, whereas identifiers don't. Well, we'll have to see how we handle that. And then the floating point number, which is covered by this this regular expression here. So it handles floating point numbers with E in them and so forth. Let's test that out. Let's 2.6 E negative 12. And if we run that, and it got the 2.6 E negative 12, so that was properly parsed. You see, this is printing out a real float here. Where if we went 22.6 E minus 12, it's going to change it to 2.6 E to the minus 11th. See, it normalized it because this is an actual float that's being printed out. This is just text that's being parsed. So that part of the parser is working correctly. and we're not handling identifiers yet in our parser. And I think we'll be doing that in the next video because we're sitting right at 20 minutes now. So I'm going to end this video here. What we did in this video really was we added this capability in to print these out so we can see them, so we can see what's going on in our abstract syntax tree and prove that it is in fact compiling the abstract syntax tree the way it's supposed to. In the next video, we're going to flesh out our language a little bit more. We're going to have a call expression, and we're going to have a prototype expression going on so that we can make functions. Prototype is just that. And actually, I need to do a function as well. Oh, there's function AST. So we'll have a function, we'll have a prototype, and we'll have a call. And that way we'll be able to make functions with expressions in them for now. And they'll do something that those expressions say to do. And we need to add other things, control structures and other stuff. We'll see how we're going to do that. We'll work that out in detail. So thanks for watching. I hope you liked it. If you liked the video, hit the like button. If you really liked it, hit that subscribe button. And I'll see you in the next video. Thanks for watching.